So in this video I'm going to show you how to align two structures, two polypeptide chains which may not have any sequence homology, and so I'll be using the Kpax program from the Structural Bioinformatics Library under VMD2. And so I'm going to the plugins menu and I'm opening the GUI of Kpax, so there it goes. And so I'm going to select two files. So the first one is one fxi.pdb, so this is a ferrodoxine, a protein molecule involved in electron transfer in a number of metabolic processes. And the second one is 1ubq.pdb, so this is ubiquitin, as you know, a protein involved in protein degradation as a marker. So I can load these structures under VMD, and in doing so, in fact, it's impossible to conclude anything because, first of all, the molecules are not in the same coordinate system, and secondly, one asymmetric unit has a single chain while the other one has four of them. So I'm removing this from VMD, and instead I'm going to compare the chains A in both files. So I run the calculation and within a couple of seconds I'm getting the alignment here and the statistics. So as we can see, we are told that 96 residues from ferrodoxine and 76 residues from ubiquitin yield an alignment of length 62 for a Lister MSD of 2.76 angstroms, which is pretty low, given that the sequence identity score is as low as 8%. And the similarity score is 26%. So in this middle section we see the alignment. So for example, the first line tells us that res ID3 from ferrodoxine goes with res ID1 from ubiquitin, and so at the very bottom we get the last pair aligned. And finally on the right hand side we see that we have three stretches on ferrodoxine matched with a single stretch along the sequence of the ubiquitin. So let's now inspect the 3D graphics. So I'm going to remove all these selections, or to hide them, and so we'll come back to them in a minute. And so the first thing we are going to inspect are the structures themselves. So here is ferrodoxine, and now here is ubiquitin. And so we see a beautiful alignment, and indeed the two proteins have the same fold. It turns out that this fold is named beta grasp fold because the beta sheet, which we see on top here, is trained to grasp this helix, which we see from above over here. And so, of course, with the same fold, we get this low Lister MSD we have already discussed. So if I'm removing these structures themselves, it's quite interesting to inspect the backbones which have been aligned. And so here we see again this beautiful alignment with the strengths, beta strengths which have been aligned. And yet we see that at the end of the alignment, in particular in this region, we have a gap between the amino acids aligned, and so we can inspect this a bit more carefully using VMD, for example, mouse, label, bonds, and I'm going to click this carbon atom from this carbonyl function. So this is a leucine 71 in ubiquitin, and here I'm clicking the same carbon atom from this carbonyl function. This is lysine 91 in ferrodoxine, and if I put the display background in gray, in fact we are going to see the distance, which is 4.74 angstroms. Okay, so indeed we have a gap in this portion of the alignment, and so we can try to spot this pair in the alignment itself. So lysine 91 and match with amino acid 71, so this is the gray line I'm outlining in the alignment. Let's move back to the graphics engine a minute. Okay, I'm putting back the background in white, and so as a final inspection it's quite interesting to try to spot the connection between this alignment and the het atoms which are found in ferrodoxine. So as I told you, it's involved in electron transfers, and so if you inspect the PDB file you will see that there are het atoms which are sulfur atoms and iron atoms, and so we are going to try to spot them, making a selection. And so I'll be saying name Fe1 or name Fe2 or name S1 or name S2, And if I want to make a selection of these 8 atoms nearby chain A, I'm going to say and within 5 of chain A. So this is my selection. I'm going to display it in CPK mode. Okay. And so now we can see the atoms over there. And so let me change the coloring scheme in order to use the chemical element. And now we see the sulfur atoms in yellow and the iron atom in brown. And so this is an illustration to show you that indeed one can superimpose the alignment itself, namely the backbones which have been aligned, some specific features of the structures, for example here the het atoms, in order to investigate carefully, in fact, the biochemistry. And to conclude, we can take a look to this directory here, which has been preset, and if I'm going there, in fact, one finds the files which have been generated. In particular, we get kpax-scores.txt, which is a file in which one finds the scores generated by the algorithm itself, so as to explain the final alignment. And in fact, in a minute, let me explain you what the algorithm does. In fact, this is an iterative algorithm, a little bit like the one used to compute TM scores. And so it does two things iteratively. First of all, using dynamic programming, it computes an alignment, and then given this alignment, it computes the optimal rigid motion superimposing the regions which have been aligned, and this superimposition is used to compute the next alignment using dynamic programming.